Correct problems. All right. 5.1, covered friction. Okay, we talked about the two new types of friction. Talked about static. Talked about kinetic. We inserted some equations. Remember that friction's always the lowercase f in the situation. Ooh, these markers are pretty. Okay. We talked about how to actually calculate what friction coefficients were, or using coefficients calculate what friction forces were. From there, we talked about the difference between Fs and Fs max. So a lot of times when we're calculating Fs, we're really looking for Fs max, but static friction is adjustable. Okay, so let's think about our first scenario. Simple scenario of a box on the ground. Let's say this is a box, wooden box. Wooden box that has toys. It's fine. Toy box. All right, toy box.
I'm sorry, I would like really escape my mouth.
It was unintentional. All right. Wooden box on carpet. Remember that when we talk about friction, the surfaces matter. What the object that's sliding is going to be made of and what surface it's actually sliding on matter. When we go through these scenarios, we talked about how static friction builds up to a certain point, and then it gets overcome and becomes kinetic friction, right? So static friction, say that this is our F of our push. Tiny person trying to push the toy box across the room. Friction would oppose, let's say the person is only giving us a 20 Newton push, and the box doesn't move. Okay? If the 20 Newton push and the friction force are the only two things that we have to worry about in those two directions, then the push equals friction. In this case, because it's not moving, it's static friction. Okay? Up until a certain point, right? So then let's say we increase how hard we're trying to push the box. Let's say we double our force up to 40 newtons, and the box doesn't move. Okay, then our F push, oops. Oh my God, I love the marker right now. I haven't used new markers in a while. Right? So static friction is the one that can change, depending on how hard the applied force is. Okay? Kinetic friction, so kinetic friction means that the object starts to move, okay? Once the object starts moving, Fk will be constant. So let's say we push with a force of 60 newtons, and the Fk is 30 newtons. Then our Fnet, you remember like Fnet, et cetera, okay? So let's draw ourselves a diagram. I'm going to draw a diagram of the kinetic situation. Remember that when we draw free body diagrams, all forces should be diagrammed. So this is going to be normal. This is going to be weight. Hopefully we feel pretty good about free body diagrams at this point. Who's that? Office runner? Thank you.
I thought she was going to be cool.
Oh, that's good news.
I see office runners now and they give me anxiety. Yeah, I was like, yeah.
Hey, it's Blaine Christie's book.
Hey.
Thanks.
It's infected, don't touch it.
Obviously. All right. I'm kidding. I'm totally kidding. All right. So when we see our free body diagrams like this, remember that one of the things we need to be able to do is write out scenarios that say F net X, F net Y.
Oh, I forgot about that.
Oh, yeah. Once the object starts to move, okay, once the object starts to move, let's say it's not moving in a constant manner. What you looking for?
I'm just kidding.
Sympathy candy. Once the object starts to move, if it's not moving in a constant manner, okay, so remember that constant means what? Constant means V is going to be
Equal. 0.
okay. So remember these two scenarios. I'm going to erase the wooden box. I mean, we're going to have the wooden box. I'm going to erase the description of the wooden box. Right now. We'll come back to it. Quick aside to remind you. F net equals MA when non-constant motion. F net equals 0 when stationary, so not moving, or constant velocity. Okay? And remember that it's because constant velocity means change in velocity is 0. And the acceleration formula says delta V over time is going to be a number. And if your delta V is 0 because it's constant, then A is 0. Make sense? So the reason why F net is 0 is because when an object is moving at a constant velocity, it's not changing its velocity, which means that acceleration doesn't exist. MA is going to be the more complicated of the two situations. So when we're talking about our box being pushed with a friction force opposing it, so now we've changed our scenario just slightly, moving away from static friction into kinetic friction, what do we know about the net force in the x direction? Do we think it's moving constant or do we think it's changing? We're changing, right? Because we're now accelerating this box. Once we start pushing it, it has to start moving, right? And that start of the movement is going to be some kind of an acceleration. Yes?
So, like, when they present the problem to you,
Yes.
what's really the difference between what they'll give you for a constant motion and what they'll give you for a constant velocity? Like, if there was a constant velocity, would they just tell you? Whereas for a constant motion, you might have to think about it.
They're the same. So they would, I mean, you would be given some information like, oh, and it starts to move at like a constant speed. A lot of times they're going to say something about constant speed or constant velocity. And if it's constant velocity, constant speed, constant motion, then you know that your net force is going to be 0. Okay? Otherwise, your thing is probably accelerating. And a lot of times they'll say, like, what is the acceleration of the system? That should give you the indication if someone asks you for an acceleration that something has to equal mass times acceleration. Otherwise, you don't have acceleration in the problem.
So when you say that you use the F net equals MA for a constant motion, you mean if it's accelerating?
Correct. So the constant motion, I'm sorry, wait. F net equals MA when it's not constant. F net equals 0 when the motion is constant.
Oh, okay.
So think car moving at 5 miles an hour for 30 miles. That's constant speed, right? Mm-hmm. So that particular situation, there's no acceleration happening. So that would be 0. Whereas when the car starts from a stop and tries to accelerate up to 5 miles per hour, there's an acceleration over that course of that part of the motion.
Okay.
Make sense? Okay. So in this particular case, we're starting to push the box. We've overcome the static friction. We're starting to push the box, which means there's going to be an acceleration involved. We also then know that in the x direction, what expression can we derive from our free body diagram? Remember that forces that point to the right are positive, forces that point to the left are negative. So what can we write using this? The thing to the right.
F push minus FK.
Right. F push minus the coefficient of kinetic friction. So this is our review from chapter 4. Right there. The new stuff is in trying to figure out what the coefficient of friction is, or trying to figure out what the friction force is given the coefficient of friction. Okay, so now here we would have to, now I guess the next question is this box moving in the y direction?
No.
So what would we say about F net y? 0. what does that mean with the expression? Up is positive, down is negative. So what do we write? N
equals W.
minus W. And then, because 0 equals N minus W, N equals W. So you were right. Okay? Okay, so now we have a couple of different expressions that we could use to actually solve some information. But I haven't really given you much of a question, right? We're just talking about what these forces do and how they interact. So now let's say that the force of this push and the box starts to accelerate once we push it, okay? Let's say that we push it with 60 newtons of force, okay? What other piece of information do you think we're going to need in order to solve this problem? The weight, or more specifically, the mass of the box, right? We're going to need the mass of the system. Let's say 25 kilograms. Okay. I'm going to erase some of this discussion on static friction because we're not really dealing with a static friction force right now. Okay. So we have these expressions that we can use to solve for information. I'm going to say that our overall question, and we're going to give ourselves a couple. One is going to be, what is Fk? And the other is going to be, what is A? I think I gave you enough information to do this. Okay. All right, so we don't need this or this. We do need this, right? Do you agree? Here's my two expressions. We don't really care about this part. It's just kind of a let's start with the thought exercise. All right, so what do we want to solve for first? We want to find friction, right? Mm-hmm. So if we want to find this, what do we need? So we're probably going to need N, right? We have an expression for N equals W. We also need mu K, and we were told it was carpet. It was like wood on carpet, right?
Yeah.
Okay, so we got to find a mu K for wood on carpet. Okay.
Oh, and the chart?
Yeah. So someone look at the chart, whoever has their computer open, find the coefficient of kinetic friction for a wood box on carpet, and then the rest of you solve for normal. So if N equals W, remember that the formula for W is mg.
I don't see one for wood on carpet.
No?
I see wood on wood, and then waxwood on wet snow, metal on wood.
Waxwood on wet snow. Okay, hold on. I'm going to use the great Google. I got wood on carpet for kinetic friction is 0.8. I got 0.8.
For the N, I got 245 newtons.
All right, and we got 245 newtons for N. Okay, so now let's get F, because that's part A. Yep. I might have to change my F push because I think it might be too small.
I got 196.
You got what?
196.
Cool. This is the hazard of making up numbers when you start a problem. This is going to be 300 newtons instead. Woohoo! Because we need our push to be larger than our friction, right? Otherwise, we're going to have a negative number. And when this person, so if we think about this situation, if the push minus friction comes out to be a negative number, then when we're pushing forward, we're saying we're accelerating backward. So that's not really going to work out for us. So we got to make sure that this particular thing works out. Again, hazards of making numbers up without doing the math in your head. Okay, so now we have our friction force. In part B, we're supposed to be finding A. So we have this one. We use this.
Mhm.
So we can do MA equals F push minus FK.
Where does the 245 come from?
That was the normal that she calculated
Okay.
by taking the mass 25 times 9.8. It's a big box. This is like a really heavy box. Sorry. This is a solid 40, 50 pounds. All right, so what do we get?
4.16.
Sounds about right.
Yeah, I got that.
Remember, it's meters per second squared. That box is going. First off, we don't have a 50-pound toy box, but it's fine. It's all good. All right, so that is the basics behind our friction problems. Okay, so why don't we do a problem where our friction is not enough to overcome? How about that?
So static.
So we want to do a static friction problem. Let's do static friction problem. Yes, ma'am.
Oh wait, I don't know if it's still.
I'm gonna find one. I'm not gonna make one up. Go ahead.
I was gonna say, I was gonna ask if you could do another ethnic this thing equals 0, but I don't know.
So that's gonna be the static friction problem. Yeah. What's up?
So where do we put 300 if we go to 245?
The 245 is the normal force.
This was the normal force that we calculated.
And we just like chose like 300.
Yeah, 300 was the given.
Oh.
300 is
correct.
the push.
Yes, ma'am.
So basically, F net equals 0 when we do static friction,
Correct.
and F net equals MA when we do kinetic.
In most cases, I would say yes.
Okay.
It depends on the situation.
Okay.
Because remember, you can have a situation where net force is 0, but the object is moving
Because it's a constant velocity.
because it can move at constant velocity. In that case, there would also be kinetic friction.
That makes sense.
Okay. All right. Let's find you a static friction problem. Let's do a static friction problem. It'll be fun. It'll be a good time. It'll be fun. We got this. Okay. Okay, like that looks not tricky. I don't know. All right.
What are those little jars hanging? They look pretty.
Oh, they're like it's like a set of lights. They were Halloween potion lights, but I feel like it makes a lot of sense in the chemistry classroom.
I do like them. They're cute. Did you make them or did you buy them?
Heck no, I bought them at Meyer.
They look
Alicia, what'd
cute.
you get from Starbucks?
Well, I asked for a peppermint mocha, but when she handed it to me, she said, "But here's your peppermint latte." And
Do you like it better?
I don't think it's a latte.
Oh.
It's very confusing because like a latte wouldn't have chocolate syrup or whatever in it. And I can taste that there's definitely sugar in this
But
thing.
there's no chocolate in it?
No, there is.
There is.
There is, but I think she called it a latte even though it was a mocha. That's what I'm saying is like, it's okay. All of the Starbucks people that I know that work at Starbucks are like, the Meyer Starbucks is the worst. But I had to get dry ice for the dry ice lab, so you work with what you're given. We did the dry ice lab this morning. It was a disaster.
They have Starbucks.
There's 20 of them and one of me.
I did not know that.
Okay,
You can buy dry ice at Maya.
yeah, whole big bags of it. It's kind of pricey, but I bought 6 pounds for $15, and then I bought another like 4-pound bag for like I think it was like 8 or 9. Yeah. I mean, it's nothing if you want to have a good time on a Friday night and like throw it in
Oh, you're saying the salt.
buckets of water, I guess.
Thanks for the idea.
Yeah, when I'm bored this Friday.
Put it in some. You could also definitely put it in a toilet and see if you freak your mom out. Like,
Oh, that would be
Dad did it
so
for senior prank. He put dry ice in the baby toilet. So then there's like,
ooh,
Yeah.
okay,
It hurt
Let's
really
go.
bad.
I found one. Let's do it.
If you guys put it in one day,
It's another wooden crate. This time it's full of MacBooks. That's what I have to say. Well, it's gotta be heavy.
We should do dry ice.
A crate of dry ice.
Yes.
let's just have it filled with raw.
with rock?
Yeah, rock box.
Did you say rocks? Just rocks? You just want to... Okay, here we go. We're just going to say it's a mysterious 120 kilogram wooden crate.
Sounds like it has bombs in it.
Wooden crate is resting on a wood floor. So it's wood on wood. Oop. All right. What maximum force can you exert horizontally on the crate without moving it? So the first thing you should see is the term maximum. Right? And we have one formula in this particular section that has the term max in it. So a maximum force can you exert horizontally on the crate without moving it?
So that's static.
Yes.
Okay.
Okay, so fair warning, I'm probably not going to get to talking about, what was section 3? I'll be here after school if you want to come and see me. We can talk about it after school. Section 3 was on Hooke's law. Okay? Drag forces are going to be something that I'm hoping you can just do yourself, because remember, it's just like a bunch of variables. Plug in the right number for the variable. You'll be given the equations. Okay?
Oh, okay.
I feel like drag forces are also something you really probably don't need a ton of time on. One of the things we'll go over is like the difference between solving for FD and the difference between solving for V. And those are the two equations in that chapter. Okay? All right, so, because I feel like friction is probably one of the more complicated of the three things that we're talking about in this chapter, and you probably need more time on it. Let's draw ourselves a picture. No, let's start with the picture. We're on a horizontal surface. We're trying to push it. We have friction going the other way, and our goal is Fs max, right?
Yeah.
So it says, what is the maximum push that you can exert on this box without moving it? That's our goal. We know that mass is 120 kilograms. What is mu of the wood on wood?
I will check.
Okay.
That was so like,
She's like, I got this.
0.5.
Okay. Okay. So, first things first. Do you agree that this is a static friction situation?
yes.
Yeah.
Because the object is not going to move.
Exactly.
Okay. Do you also agree that it's a maximum static friction problem?
Yes.
Because it does say what is the maximum force you can exert. If you exert anything beyond that maximum force, the thing will start to move.
Yes.
Okay. So then we've got our diagram. Draw yourself your free body diagram from that diagram.
I'm so mad at these.
Why?
I don't know.
Gotta get used to free body diagrams.
Like, why did you flip them? Like, I don't understand why you flipped
Oh, because the push points to this way,
Oh, yeah.
and the
okay.
friction points opposite of whatever your push is.
them. Okay.
Sorry, this is like the visualizing. This is how they would all actually interact with the point S.
Okay.
Because we always draw forces coming from the center of the system.
Yes.
Does that make sense? So your diagrams, so like your pictures in this chapter are always given like this. Or you'll see like the person, and he's like pushing down on something, and the object he's pushing down on is the thing we care about. Does that make sense?
Yep.
So then when you redraw this person's push is down in this quadrant, and not pointing this way. You never want the arrow to end in the middle. Make sense?
Yeah.
Okay. All right. So here we are so far. What do we know? What can we do next?
Normal is equal to weight.
Good.
So we can figure out the weight with the mass.
N equals W, primarily because F naught in the Y is equal to 0, is what she's saying. How often are we going to get to assume that F naught in the Y is 0? Pretty much every single time. Because our objects don't move up and down, they move left and right in our problems. All right. What else can we assume?
That F push minus F max
Mm-hmm.
equals
What do we think? Is the system moving?
Oh, I meant.
No. Is the system moving?
No, 0.
Our goal is to keep the box from moving, so then the net force should be 0.
Is it all because it's
Right, because we're trying to figure out what the maximum static friction. Okay, so then if we have this, we can also say that. Do you agree?
Yeah. Yeah, because it's not moving.
Okay, because it's not moving, and because it equals 0. A lot of the questions you ask yourself in physics are, is it moving or is it not moving? The situation matters. Okay, so here's our 2 equations, all right? In order to figure out what the force of the push is, because this is our goal, all right? That's our overall goal. That's the thing we don't know. That's the thing we need to find. We need to know what Fs max is. And we have this equation that says that we can take the coefficient of friction in the static times the normal.
I think I got it.
But we need n. How do we get n?
Find weight.
Find the weight.
I got
What'd you get?
1,176.
Olivia with the calculator. So then this. What?
She said, go girl.
And then we get Fs max equals what?
588.
588. Cool. Okay, so then our F push just has to equal 588. Okay, so if I push on this box with up to 588 newtons of force, okay, the object will not move. If I push with 588.1 newtons, what happens? It starts to move, and we have to do a whole nother calculation. All right. Let us move on. We good? Can I erase? All right, let's talk drag.
I think the drag queens.
I know.
Was that like
Isn't that
5.1 slash 5.2?
That was 5.1.
So what's 5.8?
5.2 is drag.
And then
Drag
3
forces.
plus
Okay. First things first. Only happens in what? In fluid. What is a fluid?
Liquid and gas.
Thank you.
Go crazy.
AKA liquid or gas. Okay. Next thing's next. In drag equations, we can calculate the force of drag on an object using this equation. Okay, so that's the drag. Ooh. I feel better. I'm sorry. My Starbucks has been partially blocking some of my video, you guys. It's all good. If you have questions, you ask. Okay. So this is the first part of the drag argument. How to calculate the force of drag in a fluid, okay? When an object is free falling, through the air, through a fluid, whatever you want. Most of the time it's air for us, okay? The weight is going to be the only force acting on it, right? So think about when when you drop an object from wherever, the only thing pulling it is the weight force back to the ground, right? That's mass times gravity. Okay. Because of this, these objects have what we call terminal velocity, meaning they cannot move any faster than the fastest speed that gravity can pull it. Okay? Most objects don't hit terminal velocity before they hit the ground. Really, the only objects that do are things we like throw out of planes. People, crates, you name it. Okay? If we want to find the terminal velocity of an object, we can make the assumption that this whole equation equals weight, because the force of drag is the only thing pulling it down, which is the weight force. And then we can rearrange to solve for the v in this equation. Okay, and this is where we get this fabulous v equals 2mg over cpa. Same exact variables as up here, okay? Except for obviously gravity and mass. Okay. Correct. So that's when it's falling through air and you're trying to figure out how fast the skydiver is going or how fast the plane is falling out of the air.
So when are you just going to use the force of drag equation?
If you're asked to calculate a drag force, this is the thing that you want to use.
So that would be for like a car.
Right, that would be like a car traveling on the road. Okay? This could be anything from a car traveling on the road to a boat traveling through the water to a person falling in the air. You could calculate the drag force of somebody falling if you wanted. It should just be equal to the object's weight, but whatever. And then for this guy, it's how fast can the object move? What's the fastest speed it can move if the only thing acting on it is gravity? Okay? Did you have a question? Okay. There's one more equation in this chapter, or in this section. Can I erase? We good? All right. And it is Stokes' law.
You didn't erase the top.
I think last semester she threatened to like blow a gasket if I didn't go and fix.
It just bothers me. That's all I would look at. So they,
I mean, some people just want to watch the world burn. It's fine. I'm one of those people, 100%.
Viscosity.
Viscosity of the fluid.
Oh,
Yes. And V is the object velocity.
I've been waiting for you to explain this
I think the rule, it's like
because
shaped like an N, but
Stokes' law? Wasn't it in the lecture on section 2?
alphabet.
We learned this in 8th grade, you should
Oh, this is like
I
a.
don't remember. I thought you did, to be honest, I forgot.
I'm pretty sure
I know beta.
I googled what this meant.
I
So
know
this
alpha,
so this
and omega.
law is only for
Viscosity.
when dealing with a fluid denser than air. Where viscosity matters.
Okay.
Do we understand the difference between density and viscosity?
No.
Okay. So have you ever seen molasses before?
Yes.
Oh, yeah.
Okay. So when you think molasses, do you think it moves faster? Do you think it moves slow?
Slow.
Moves very slow. Okay. That's because it is a very viscous fluid. Okay. When you hold it, though, it's probably not the heaviest substance you've ever held. That would mean it's not the densest substance you've ever held. Viscosity and density do tend to go hand in hand. So a very viscous fluid is often also very heavy. So think about like syrup and it flowing. It tends to have some heft to it. And if you compare it like the same volume of syrup to the same volume of water, the syrup's probably going to feel heavier. Okay. So density and viscosity do tend to go hand in hand. But resistance to flow is what viscosity is, and how heavy per volume, like how many particles take up one area and how heavy they are in one volume, is the term for density. Okay? All right. So, we would only use Stokes' law in very specific, very specific scenarios. When they're very, very small, okay, so like microparticles, how they move is very different than like how your shoe moves through the air. Like you throw your shoe, you're not going to really have trouble explaining the motion or describing the physics behind throwing an object. But if you can't see the object, it behaves very differently. So think like pollen. Pollen particles are so small that we can't describe their motion very easily because they're harder to see. They also don't behave the same way. They're not as heavy. Okay? All right, so that's Stokes' law. That's section 2. With section 2, it's plug and chug. There aren't really like special, let's draw a free body diagram, let's figure out the scenario, let's break it into components. Like there's not stuff like that really from section 2. Section 2 is really just introducing the idea that there are different forces that are not just friction-based. Drag is a force that is not contact-based. Okay, so these are the two forces that we've studied so far in this chapter. Contact-based and not contact-based. Contact-based means two surfaces are in contact with each other trying to roll past each other. That's our friction. Non-contact-based are objects moving like through the water, okay? We're not talking necessarily about the boat that hits the water. We're talking about the people in the boat who are not in contact with the water, okay? We're talking about the things that are exposed to a specific fluid. Okay, questions so far? Yeah.
Are we gonna have like any of those like tension problems with friction?
No.
No. Okay.
Did we do tension problems with friction?
Yeah, we did a little bit.
Did we?
Yeah, we did. In my examples, at least.
We did like...
I definitely did not.
So then the last thing on your quiz that you can expect is to be able to talk about
Oh, okay.
Hooke's law. You did this with your rubber band experiment?
And our openers, right? Our openers have been.
Yep, our openers have also had some stuff to ask you about Hooke's law. Yes. Just real quick. The force that pulls on something stretchy will deform that object, that delta L, is the deformation from its original position. K is the proportionality constant. And remember that proportionality constants are object dependent. So a rubber band is going to have a proportionality constant that is based on how thick it is, how big it is, how great the rubber is compared to like if it's like cheap rubber or good rubber, if it's made of one substance versus another. And remember that we talked about this during lab. We can use proportionality constants to kind of like describe stretchiness. I don't think I'm spelling that right, but your proportionality constant gives you an idea of how stretchy something is. Okay, and we talked about the graphs with this. This was like our big...
And that has no, what's it called, label?
Right, K is the slope of the line. So with greater forces, objects that do not deform as much are not going to be very stretchy. Okay, so the steeper the slope, right, the more stretchy the object is, or the more able it is to be deformed and come back to its normal. Does that make sense? Mm-hmm. Greater the slope, so larger K equals more deformed. Okay. Yeah.
If it's in centimeters, you need to convert it to meters.
Correct. Remember, that's one of our standard units.